in the past with Mathematica in the Wolfram language, but rather about data, scientific and mathematical data. Something that over the last 10 years nearly have been slowly introduced in the Wolfram language and have become more and more powerful as a real tool to do useful calculations. Okay, so let's start with comparing mathematics versus describing the real world. Mathematics is basically a set of human-selected axioms and a set of logical inference rules. We have algorithms, theorems, we can derive them, we can prove them, and also there are various schools of how to approach mathematics. More or less everybody agrees on this, if this is the Brouwer intuitistic versions or Hilbert more formalistic existential ones. We can prove everything, we can derive it. And mathematics is either constructive and computational, something that Mathematica has been mostly exploiting, or it can be much more existential and formal, thinking on the Bourbaki school. The real world is a totally different business. It is made from a vast amount of totally different things. And it cannot be redefined through different axioms or definition. It is just what it is. It is sometimes very hard to describe it because it's not unique, it's fuzzy. It's very difficult to formalize. For instance, you have a picture of a room. How would you ever formalize this in a language, in a computer language? Or you can always check if something is a real number. But what exactly is a train? Like, how far does a train go? Is this object to the right still a train or not? And there is a very complex hierarchical structure in the real world. For instance, if we go from a painting to the whole building, how are they related to each other? It's very hard to get quantitative data about many parts of the world. For instance, recently I needed for some project to know what's the amount of light that comes out of a firefly. It seems like a very simple question, and it seems like you just go to Google or any biology book and look it up. You will find it's very hard to find. And the only reference I ever found is a small German booklet from 1910. Nobody ever has measured it before or after. So the real world is really concrete, messy, but of course the real world is really important. That's why we have somehow to deal with them. Because the purpose of science is to predict the result of possible experiments, at least according to some relatively conservative Copenhagen School of Physics in the Bohr-Heisenberg line of thought. So to describe the real world, we must add to the Wolfram language things that Mathematica didn't have. For instance, physical quantities and their values are measured in units, so we need units, something that we added a while ago. For socioeconomic sciences, life sciences, geographic sciences, we need things like dates, or we need positions on Earth. We need to have counting units, like while watt, meter, kilogram are nice physical units, in socioeconomic science we have things like how many divorces per 10 years and 100,000 marriages. So things like divorces and marriages must become some kind of units, and we must be able to deal with them. We must be able to describe, visualize events, historical, wars, sports. And to do this, we need a whole set of different machineries, which approximately can be grouped into four things. A, we need computational algorithms and efficient data structures. A lot of this is in the Wolfram language in a long time. For instance, functions like desolve, solve, desolve are, of course, perfectly suited to describe the real world, especially physics, chemistry, and biology. But we also need things like time series and probability distributions, because frequently real-world data are not quite exact, they are fuzzy. And because of their fuzziness, an increasing importance comes to machine learning techniques where we have the first two functions, classify and predict. To represent the real world semantically, we need, as I mentioned, dates. We have the function date object, positions on Earth, units, measures, and we need a thing, like a city, a type of a car. I will speak about this more later. Then we need the actual data about the world. We have a thing like a river, an animal. We need to quantitatively describe it. How tall will it get? How many babies will it have? How long is it pregnant? And so on. And of course, the data about the real world must come from somewhere. They are not kind of nature given mathematically, so we must import them. We must import them from a wide variety of file formats. Some of them change on the basis of seconds or sub-seconds, like financial data. So we need to be able to connect to such things in real time. Some of them are given through natural language, not a nice piece of code or a number. So we need functions like interpreter, or maybe all what we sometimes have is just an image, and we still want to understand what it means, so we have functions like image identify. But in addition to the real world, there are actually also from the non-real world objects that in some sense have qualitative and quantitative properties. Mathematics itself, while there are algorithms, there are also many named things in mathematics. Theorems that are named after people. We cannot derive them what's the name of the theorem is. So we need a database of such things. Then there are many things that are abstract and very foundational for human communications, like we have words, alphabets, characters. Would be nice to have all of them in a coherent, uniform way, computationally accessible. And there are, of course, the named laws, equation models of physics, chemistry, and so on. And then there are such things which don't seem like, from a scientific point of view, the most important thing in the world, but for instance on the Wolfram Alpha website, they are very popular. They are fictional characters. Like people ask, how old is Gandalf? Or how tall is Lord Voldemort? If you look at the taglines that were associated with the Mathematica over time and or the Wolfram language, you see a very quiet change. In version 1 and 2, the tagline was a system for doing mathematics by computer. So it was really focused just on mathematics. Then in the next versions, it slowly changed to an integrated environment for doing technical computations. That's already surely much broader because it surely already includes engineering, chemistry. And the next versions weren't so clear about the tagline, they was never so emphasized, but since version 10, there's again a clear tagline, a technology stack for doing knowledge-based programming. And the knowledge-based emphasizes there is something that comes from the outside that is not just algorithmic. And that's the part I want mostly to discuss today. What is needed to do this? What did we have to build? How will we continue? And how is it useful? So let's look at some concrete examples. The most important function to get data that we have since nearly 10 years are the various star data functions. So if we ask in version 6, what functions are there that have the name star data, we get some that have something to do with either formatting, like box data, button data, cell group data. We get some that have something to do with mathematics, but we also have country data, element data, series data again, mathematics, polyhedron data. So we had a first collection of data function in version 6. In version 10, if you make star data, you get nearly 150 different ones. In addition, there are a large amount of infrastructure to support these. And in version 10, there's one big change as compared to earlier. In earlier versions, we didn't have units. As a result, we couldn't give you a result that was properly dimensioned. But in version 10, if you say now city data, St. Petersburg population, you get this result, which has this light gray background if you mouse over, which explicitly says people. That's not just a number, but it has a different status. Let's look about coordinates on Earth. In version 6, there was absolutely no functionality for doing anything about Earth. you see there was not a single function that started with geo and wasn't geometric. In version 7, we started with a few little things like geodestination, geodesy data. Today we have nearly 75 different functions to deal with this. Dates and times. There were obviously some date functionality back in version 6, but it really wasn't much, and it wasn't particularly powerful and expressive. Today we have more than 30 functions to deal with dates. Units and measures. Up to version 8 we didn't have anything. Everything that started with unit had nothing to do with units and measures. Today we have 45 functions including this, so around 30 functions that really deal with units. And even data structures had to be added to the Wolfram language to really deal efficiently with the real world. The most important are probably association and data set. I don't want to go long into it. For instance, we built, in quotes, a list of pairs with x and x squared, and we build this list by adding it to an already existing list. If we do this naively with join, we get this yellow curve, and for 40,000 elements it takes only a couple seconds. There's this new function version 10, association. I hope everybody is using it. It's a real nice function, very flexible and very, very fast. It's probably the single most complicated function we have in Mathematica as a pure data function. And it is vastly faster. There is a very nice screencast by Mark Sofranio from last year's Wolfram Technology Conference in Champaign. A similar function is dataset, which is a very nice, convenient way to wrap up a table-like set of data. For instance, here I just import the web page from the Wolfram site with forthcoming events, and I string split it at new lines and say the first one is the event, the second one is the place, and the third one is the date, and we see today's conference here. And once I have this data set, I can conveniently deal with it. I take everything downwards, I take just the place, then I run interpreter, which gives me a computational representation of the cities, not just a string, and then I can immediately plot it. So things work very nicely together. Similar to the association talk, I recommend from the same conference a talk by Tallis about the use of data sets. And then there are, of course, many more algorithms that were added, especially image processing and statistics, which are too far to go in right now. Since the year 2006, we started working on what is now the Wolfram Alpha website. At the same time, we started to put the star data function in the Wolfram language. Since 2009, the Wolfram Alpha website is live. Since 2011, the Wolfram Alpha function is available in Mathematica, which is sometimes very convenient. And the Wolfram Alpha function allows to access a huge amount of different kinds of knowledge. So that was very successful, and people really come to the website in large amounts. So we thought, if this is so nice and useful functionality, we should make it available in the Wolfram language itself. So since the version 10 from last year, we have this new function entity value, which I will come in much more detail later, which makes a large fraction of the knowledge of Wolfram Alpha accessible directly within the language. So just to see what kind of language knowledge is there in the language, here are a couple of popular questions that we get on the Wolfram Alpha website. So you ask, like, what are identities for the Riemann zeta function? What is a certain symbolic derivative of order n? What is the Hamiltonian of a double pendulum? When did the moon rise at a certain day? What was the solar flux last week? How many people go per week in a certain hospital? How many apples are eaten in France, Germany, Italy as compared to each other? How much calories do you burn when you do a certain exercise? And so on and so on. But as you see, most of this is more or less textual, so getting this all in a more computational form was highly desirable, something that we worked on the last years. There are various types of data. Data can be either real-time, like weather, stock, air traffic. They can be eternal, like physical laws. They can be mathematical. They can be semi-static, like countries. They do change, but over relatively large timescales. And all our data are carefully curated, checked by humans. They're interconnected, unified. So we put a lot of energy into cleaning and maintaining our data. So now let's look at a very typical result. Say you want to know in the Wolfram Alpha website about the crab pulsar. And you get its name, who surveyed it, and then you get a large amount of physical characteristic, and you know there's a real large variety of units, many that are not even SI units, but they are still the units that are used in astronomy, so we try to express it in the units that people are really using in the field, like erg per kiloparsec squares. Everybody is supposed to use SI units, but people are slow to change in the real world. Or how many golf balls fit in the Atlantic? To answer such a question, you have actually to do quite a few things. First, you must know how big the Atlantic is. You have to know how big a golf ball is. You have to know what's a typical packing density of spheres. And you might have to know that this is a type of question that you can only answer in a way that is a rule of thumb. And you can access this result directly within the Wolfram language by calling the Wolfram alpha function with a string. Oh, Galina just wrote me I should make it a little bit bigger. I will try 300. I hope this is better. And you can basically get the result directly from the Wolfram language. So now dates. Since many years we have the function date and it gives a list, but it's just a list. There could just be a list of numbers. There's no reason to assume that has to be a date. Now we have a genuine date object which just is a date. It can be nothing else. That is very nice for semantically really representing things. So here is a Tuesday, and what happens if I add 20 days? I get a new date. So there's a whole arithmetic associated with the dates. And we know what are time zones of cities. And let's see if this works. What time is it right now at your place? 23 minutes after 3 should approximately be right. So we are where a certain Mathematica potentially is, where you want to know something. We convert between the time zones. We know summer times and so on. One of the biggest additions we had to make to accommodate really for the real world was the addition of units and measures. That was a big project, and today we have probably by far the largest collection of units and physical quantities. There were quite a few people who worked for this for a couple of years. We have around 25,000 units with coming from more than 2,000 physical quantities. So what does it mean to know a unit? We must know its value and its precision. For instance, today the speed of light is an exact value versus the value of the Planck constant is known with a certain uncertainty. This will probably change in the year 2018 and it will also become exact, but there will always be some constants that are exact and some that are inexact. There are also historic units that were used a couple hundred years ago. They are not 100% cleanly defined as an exact number. They are sometimes intervals, sometimes they are fuzzy, sometimes there are two possible values. Its usage changes by country and time. We need their names and abbreviations. We need to format them. Then there are many units that have the same name, like calories. There are a large variety of them. The representation of a unit is the head quantity, and the first argument is how much, the magnitude, and the second one is the actual unit as a string. And the result is this little bit brownish looking box that has a mouse over which says what kind of unit it is. You can conveniently input it with control equal, where you can use normal language and it will understand what kind of unit you have. And since version 10.1, there's also convenient auto-completion, where we know kind of what are commonly used units that start with M, or that what are commonly used units that start with mega. Here's an example from what I just mentioned. There are many different versions. Historically, before we came to the current ohm for electric resistance, there were absolute ohms, international ohms, Bordeaux trade ohms, Reichsanstalt ohms from Germany, legal ohms. And if you just put them in, here are they look all fine. But if you look at the actual values and you subtract two modern ohms, the absolute ohm was the precursor of the current ohm, but the other ones are all slightly different, a little bit larger, a little bit. And if you come back to the Crab pulsar that I have shown earlier, and you ask what are its properties, you get this large amount of units occurring in the values of its properties. And we understand them, we can convert them into each other, we know their precision. There's a lot of additions still in modern times for units. And people come up with new ideas. For instance, some student came up with this idea, a meter, which you call the Heller meter, which is approximately the size of the universe. And he actually proposed this to the official committee of units to Paris. It was not approved, but it became very popular in the internet, so we must understand. Then Don Knuth, the famous computer scientist, he came up when he was a young student with what he calls the Brodsky system of units, and you see it's nearly impossible to even pronounce any of them, but we have implemented them all because people use them to see if we really know all units. And there are units like the Darwin that measures evolution, like how much does an animal change over 1,000 generations, which are slightly unusual units. We have the function unit convert that, as long as things are dimensionally compatible, can convert between any possible units. Like here, convert 3 inches into meters or miles. By default, we always go to SI base units. And units are supported as much as possible, not yet quite everywhere, but virtually everywhere throughout the system. For instance, I get for all metals, I get the terminal conductivity and the electrical conductivity, and then I make a list plot with a tooltip on them. And here are the various metals. But you see the axes are properly labeled in watts per meter Kelvin and in Siemens per meter. Or I have a set of pairs, the first element being a length, the second element being a mass, and I can make an interpolating function between them, and then I can call it with obviously the first argument being again a length, and I get a result. So this makes the system very powerful that you really can plug in units wherever you want. Related to units are currencies. They're kind of units. You can put them in unit convert, but there's also your own function, currency convert, if you want to more emphasize that you just deal with currency. So say you can convert dollars per hour to euros per hour, or you could also convert to per minute, or both if you wanted. As compared to the scientific units, for currencies, there's a strong time dependence. The value of a unit changes dramatically over time. For instance, I have a US dollar or 25 US dollar from 1800. Today, this would be around $500. Or I can even plot how it would have evolved over time. So it seems like the best would have been $1 from 1840, which would be $850 today. Then physical constants. Physical constants appear everywhere in physics. And there are the most famous ones being the Planck constants in red, the speed of light, the Boltzmann constant, the electron charge. Here's a small selection of famous physics equations. Let me see them really. So here's a selection of the most famous physical constants. By default, we keep them symbolically. We don't do anything with them, which I think is definitely the right thing, because if you have a complicated physics equation, you don't want to litter it with approximate values, because that's only coming from our unit systems that we use. It doesn't come from nature. So we can convert them, and if we take again the Planck constant, you see here we get this result, and if you look at the full form, we get this explicit backtick, which means this is a high precision number, or an arbitrary precision number, because we can only measure today the Planck constant to something like a couple times 10 to the minus 8. And if you compare the various constants, you see some we can measure exactly or have defined exactly, like the speed of light, epsilon 0, mu 0 is today defined. Some we can measure with around 7 digits, but the worst offender, and there's a big discussion, especially in the last year, the gravitational constant, why can we only get around 3.5 digits for it? Because every experiment that has been done over the last years got slightly different results, and nobody really knows why. And we have many more unusual physical constants, like a Boltzmann constant in various dimensions, like in 4 dimensions. We can get their dimensions by using the unit dimensions, which states for in the Planck constant is length to the 4 times mass to the 2 times time to the minus 2. And we can form dimensionless constants. For instance, this is this very classical constant that you can form in any dimension. You need the absolute length scale. And it is indeed dimensionless. And in D equals 3, our world, we recover the fine structure constant, the famous 137. Once we have units, we need, of course, physical quantities. The things that belong to the units and say what you are actually measuring and expressing. The underlying function in Wolfram language is a quantity variable. Again, it has a slightly different color. It's a slight gray. You mouse over and you see it is a quantity variable, and it's just quantity variable mass in this case. It can be used in a 2-argument form where you have the first argument some label. And again, we have a nice auto-completion. Because there are thousands of them, you get a nice convenient suggestion which one you want. And you can take them all and make a picture and see in the space of, say, kilogram, meters, where they live. And of course, they are virtually always around the 0 point of such a coordinate system, but there are quite a few of them. So here's an example how they really very nicely fit together and allow to express things as semantically rich as one can hope for. Say, we have a length x, a time t, and a frequency omega. And I take them all and write the differential equation in them. A normal harmonic oscillator differential equations. But these are now physical quantity variables, so if I mouse over, I see this. And now I stick them into DSolve. Because they are now dimensioned, the initial conditions must be again from a certain physical quantity, but the value of the initial condition must be now an explicit quantity. And I can actually solve this, and I get a very nice result, fully dimensioned, and say I then plug in a concrete value for the frequency and for the time, and I get an explicit result directly in meter. So that's a very nice functionality, and really that you see there's no cheating. There's a quantity variable on the left and there is a quantity on the right. Once you work with units and measures, something that you really want to do is dimensional analysis, or also called the Buckingham pi theorem. Like, assume there is some relation between energy and mass. So which one would it be? What would the power of C be? We know, of course, it's 2, but we can easily do this. Give me the dimensionless combinations formed from an energy, from a mass, and from a speed, and there's only one way to form a dimensionless combination. If I take more identities or quantities, say from classical mechanics, time, length, speed, acceleration, force, momentum, I can calculate them all and I get a long list of potential. And the same I can do with physical constant and can form dimensionless calculation. So units themselves, it's very interesting to see how they are actually used, because people actually come quite frequently to the Wolfram Alpha website and do unit conversions. So I have made a plot of what are the most used units. Money always starts, but then there comes many others. And it's a nice curve. It's nearly exponential how it... power law, sorry, it's Tip's law when plotted in a log-log plot. Or more graphically, these are the most common ones. You see, it's definitely dominated by American usage because of US dollar and fluid answers. And it's also interesting how people use units. For instance, centimeters are mainly used for relatively small things, not unexpected. For a little bit bigger, they use meters. For very small, then they use nanometers. For slightly bigger, kilometers. Then come astronomical units, light years. Well, of course, you can express any in any. Most naturally, use something that you have nice slot prefactors. Now, quickly about geocoordinates. So we have this function geoposition of latitude, longitude, which on an ellipsoid gives the coordinates, where it's important that the latitude is this angle with respect to the normal of the ellipsoid. It's not the one that one would naturally get from generalizing from a circle. And geographics is the main function that does a lot of computations and visualizations. I have some examples later. And there are many supporting functions that you can see if you look for all names that start with geo. So for instance, you can say the Wolfram headquarters is, which city is nearest to it? It is Champaign, Illinois, because actually the headquarters is in Champaign, Illinois. You can ask, is the Vesuvius mountain in Italy? Yes, it is. Or you can ask, what kind of things exist in a certain geographic area? For instance, take Kazakhstan and say, give me all airports that are in Kazakhstan. And you get a long list. Or you can do very precise calculations around the most precise ones that are out there on any commercial software. For instance, take two of your most famous museums, take an icon, make a picture, show them on the map, but then calculate the distance. So it's a little bit more than a kilometer between them, straight line. For extended areas, you can also do this. Like you can take Italy and Russia, and what is the smallest distance between them? Now we must go along both boundaries and must find where is the smallest difference. That's actually a non-trivial calculation. Or assume you start in Moscow and you go 34 times around the Earth. And then you go another 343 kilometers. Where will you end up? And you can calculate it easily with the function geodisplacement, which really takes very carefully into account the ellipsoidal shape of the Earth. And because of the ellipsoidal shape of the Earth, once you are one time around, you don't add up where you were, but you add up as a little bit displaced. And you see, you start in Moscow, and after 34 times, you're around here, and then we go, I calculated this 343, we literally end up more or less exactly in the center of St. Petersburg. Geographic coordinates are very important for a large amount of things on Earth, for instance, earthquakes. I can ask what were the earthquake between 2000 and 2014 in Kursk, and there were quite a few of them, especially because I only take the ones that have at least a strength 5, which are already non-trivial. And then I can make a map and I see where they all were. I can take even more if I take everything which has at least a magnitude 1, make a histogram. Or I can even do this worldwide. It will take a couple minutes before all of the data are there. And then you see very nice the zone plate boundaries on the Earth. There are large varieties of models of the Earth. Like what exactly is the semi-minor and major axis? And we have a large collection of them. You can choose whichever you like most. The difference is not gigantic between most modern ones. Here is a set of the modern ones. And I say take the Eiffel Tower. And I calculate the relative difference. And you see it's a pretty small number in meters. A forthcoming feature very soon is we have good maps of the moon and some other bodies in the solar system. For instance, here is a 150 kilometer resolution picture of the famous face on Mars. There are many special functions, as you know. There's sine, cosine, Bessel, tangent, elliptic integrals. With respect to geographical calculation, there is a very tight parallel. These are geographical projections. There are many geographical projections, around 500 with a name. We have a couple hundred right now. We are working on more. And you can, here's for instance a famous one that uses a lot of elliptic functions and which projects the whole Earth into a square. But there are many, many other ones. And it's very nice to use them. Many of them have only a non-trivial change to your local ones if the area is big enough. If you just have a local one, they're basically just what you are used to see. So now the entity framework. The entity framework is basically the carrier in the tool to get data about all kinds of things to you. So in version 9, we had already quite a few star data functions. Here's the list. And I rerun this against version 10 to see what's new, and we see we added quite a few in version 10. And I will give some examples in a moment. So if you use entity value with no argument, you get literally all the domains for which we have knowledge collected. Right now, they might get it. So we can count how many entities we have in this domain and how many properties. So I made this for all, and of course some genomic things are very common, so there are millions and millions of them, but there's not so much to be said. But then we have more than 1 million music pieces, we have 1 million species, we have a couple 100,000 genes, a couple 100,000 words, pretty much exactly 250,000 people. And now the properties increase. Like we know quite a few things about the people, where they were born, what did they do in their life, who were their spouses, what objects did they produce, books, theorems. And you can make the whole table, add it up, and you get a pretty stunning 230 million values that could you get access. Not all of them we know, obviously. There are always some that we miss because they are not known or nobody has ever calculated them. So the core object to represent something from the real world is what we call the entity. So here is water as a chemical, and you see it formats as this yellow orange box with this tooltip. This is the object that represents water as an abstract object, and we can ask for property. In an input cell, so this is an output cell, in input cell you see we add the chemical, so that's a little bit clearer what we are speaking about. And then you say, give me some samples of elements, and we get something. The most important for getting active values is the 2-argument version of entity value. And the property is represented by what we call entity property. It's also a yellow box. It's slightly different yellow, a little bit more yellow than orange. And then this one represents the density of a chemical. And then you can call them together, and you ask, what is the density of water? Or you can say, just apply the head density to the chemical water, or even vice versa. Or you can even be lazy and just say density, and you get this. And there are many other things that you can ask for, like what is the Hill formula string of water, and you can get it in a wide variety of formats. Then, in addition to entities, many entities are naturally grouped. Like take physical systems. There are quantum physical systems, classical physics. There are electrodynamic ones, electrostatic ones. There are some that have to do with holonomic systems or with unholonomic systems. So we can nicely group them. Like, give me all electric charge distributions that we currently know, and we get a list of them. And then the properties, some, as we had seen in the table before, domains have a lot of properties. For instance, for a country, we typically know 750 plus different properties. And some of the properties are not just a number, but they are complicated time series, like populations, exports, imports. So here are some of them shown. And the same, a property of an entity class. Like for all physical systems from classical mechanics, what can we say? Each of them must have a degree of freedom, and each of them must have some action functional. So if you have an entity and you want to know what kind of property they have, you can either ask for a concrete one, or sometimes you might want to know everything at once. Then you can use entity value with the second argument property association to get a long list. And here are a couple of examples, like here's a broadcast station. It says where it is, what power it is. Here is a pipe organ. It says its typical frequency. Here is a little cat, how big it gets. Here's the aircraft, how fast it is, how high it is. Here's a coin. What is its nominal weight, thickness? Or the troposphere. What is it in the atmosphere? A soccer ball. Sport objects are typically highly regulated with respect to size, weight, pressure. So we have collected them all and they're nicely accessible. Sometimes you want to qualify more, like population. You just don't want all of them. You want to know the population resource by age, by when it was, by gender, by race, if they live in cities or not. So you can many detailed information get out. And sometimes you might even want to know what exactly do you mean by this? Like what do you mean by race? And you can ask for a definition and you get a definition what exactly is returned. Similar to property association, there's also this entity association where say you want for all planets, you want the mass and you want it nicely annotated. You say entity association, you get this nice table. Or a more complicated example where you get a time series. I want for the top countries how much beer they consume. And here is a graphic. We see Ireland wins, followed by the Czech Republic, Belgium, Netherlands, and Denmark. You can, of course, get things back in our already earlier mentioned data set, which looks very nice and is convenient for a quick look. Like all cats, what's the maximum weight of all cats? And you get this relatively nice table that's not even complete because we have so many cats. You can also fix the reverse, fix the entity, look for their properties, and get everything again. So here, for a single cat. So I didn't put everything in the data set because it would have been too big. And then we can aggregate. Assume we have a whole entity class like Europe and we want to know the total. So we don't want first to get all individual values and add it up, but give me everything at once. So you can immediately give a total argument. You can filter things. You can filter by a variety of things like the name, or by the physical quantity, like what are properties of countries that are measured in person? And here's a long list of them. Or what are properties of countries that are measured by a certain physical dimension? And one forthcoming feature, hopefully there within the next weeks, some domains are pretty big. You've seen we have hundreds of thousands of elements, but sometimes you're only interested in a certain subset. And you don't want to get all of them and then wade through and take out what you're most interested in, but you want immediately to accept them. And there is something forthcoming which we call implicit entities. It's basically just an entity, but the second argument is not just a name, but it's a description. In this case, I want all elements that have a density between 5 and 8 grams per cubic centimeter. And what I get back is again this yellow orange box, but now with this little sign here, which means there's a collection, and I can get more detailed what kind of selection criteria that, and then I call entity list, and then I get a list of all elements that fall under standard conditions within this density range. Or I can say, give me the countries so that the boundary is the longest in the world. And I get, again, the selection criteria. I can resolve it. So Canada has the biggest boundary in the world, followed by Russia, Indonesia. Or give me the dog breed that the males are the smallest or the largest in weight. And give me the standard deviation and the mean. So it's very flexible to directly access a large amount of data. Or with respect to movies. Give me all movies that have the property that Angelina Jolie was inside and they were released after a certain date, say. And then you can immediately take them and visualize them. So a couple of quick examples how to use the entity framework. that's something I just played around. I thought it was interesting, the result. I want to get songs per composer. So I take all music works, and we have, say, 100,000 of them. I select the properties, I select the length of the song, and it's interesting that per composer, the number of songs increases. I would have guessed that in the modern world more and more people write songs, but the ones that do write songs become more and more proficient and write more and more songs. Or what are the shipwrecks in the Baltic Sea? So I just call for shipwrecks from the domain shipwreck in the Baltic Sea, and I get a data set where they are, then I can plot them. Movie runtimes. What is the distribution of movie runtimes? And we see over the years it stabilized pretty much exactly around 100 minutes. There were a time where, especially in the beginning years, where people really experimented, but now it has. And then you can compare various types of movies, like thrillers versus action movies. And here's a distribution of many of them. They are yellow histogram. But it's interesting that a normal distribution, the blue one, fits it very badly. A log normal also fits it very badly. But a stable distribution, which is a relatively complicated distribution, fits it pretty beautifully. And you can get the outliers, like there is one movie which runs for 399 minutes from 1915. It's still the winner of all. And then there's a very new one which goes for 4,500 minutes. That, of course, is very well explained with a stable distribution which has only a power law decay instead of an exponential decay. Another forthcoming domain is anatomical structures. So for the muscles, veins, organs of a human, we will have a lot of their properties, how big they are, what they do, and we will have them available as 3D pictures. So you can really play around with them and can have some fun. For instance, I take the skull, the teeth, and retrieve them all, and I intentionally got the skull and then the teeth extra, and then I can add here an invisible rotation line and say I rotate them around a point, and you can open and close his mouth. So another forthcoming function which I think is very nice is we quantified so many things from the real world. So one thing natural to quantify is our own language, and there are many millions of notebooks out there on the Wolfram demonstration site, on the Wolfram library archive, on the documentation center, the whole code that is written to you build Wolfram Alpha, all is Mathematica on Wolfram language code. So we thought, what happens if we take them all and analyze them? So we did this. It's a very nice data packlet, and there's a lot of information available. For instance, here is the frequency of use in a typical piece of code, or not a typical, averaged overall. So by far the most common function of all is list. That's not unexpected because it's the universal container for everything. The second most is rule. That's also not unexpected. We needed to specify options in plots and many other functions. Then comes times, also not unexpected, power, plus. And they were all already the blue introduced in version 1. The function that basically is most popular that was not in the original version of Mathematica is alternatives, which we use a lot, of course, for pattern description. Which is, if you go back here, something like the 10th most popular function. And you see in some versions we added functions that became much more popular than in others. And of course the latest function we will see, it must get a year or two usage so that we can analyze what people did with it. So then mathematical data. So far I have mostly spoken about data about literally the real world, but we have a lot of mathematical data. For instance, we have minimal surfaces, we have their names, we can easily get some pictures of them. We have plane curves, There are many of them. We have quite a few properties of plane curves. Here you see them. And here's a quick table that you can conveniently make. Say take an ellipse and you get the algebraic degree, the arc length function, the area, a picture, the involute, the normal vectors. And they're all standardized across all, so it's very nice for direct use. One thing that's important to note is if we return the population of a city, it's more or less just a number or a quantity. But if we return a mathematical formula, the result must contain a variable. But in which context should this variable live? A user uses the global context, so we do not want to interfere with it because the user might have given the variable a value. We also do not want to use a newly made variable in the user context because the user didn't make it. And we also don't want to use a system variable that we create automatically on the fly. Fortunately, since a couple of years we have these formal variables. You might have encountered them in functions like desolve, product. So these are these variables which have this dot above and below that live in system, but they cannot be assigned a value. So all mathematical results are returned with this head function so that you can conveniently apply it to whatever variable you have, and inside it uses a formal variable so that no variable is generated. The same here for a solid. Here are some Steinmetz solid. You get its volume and an inertial tensor around the principal axis. Then there are graphs. Eric Weisstein is a collector of graphs. This is a fantastic collection of nearly 6,000 graphs with around 180 properties for each, which you can nicely, quickly search and visualize. Here's just the results for one single of the graphs. And we had a project 2 years ago where we collected continued fractions. It's interesting, like there are plenty of books about integral tables. There are plenty of books about sums and products. There are some books about differential equations. But interestingly, there is not a single book out there that has ever collected all continued fractions. So we made a collection of them and found around 11,000 in the literature. They are now all available together with where they come from, where do they converge, how do they look like, what variations of them exist, because there are a couple of methods to generate variations. And then something that's soon forthcoming, we are very excited about. So since around 10 years, we have this Wolfram function site where we have a collection of mathematical functions, their properties, and we finally made this available through the entity value function. So we have a domain mathematical function. For now, these are just the ones that are already built in, but we have in preparation a couple hundred that are used somewhere in the world that are not currently built in functions. And you see here all our old friends, binomials, error functions. There's a long list. Here are their classes. And then you can ask, give me an integral representation of the array function. And you get again a pure function. There's an inactive wrapped around because the inactive, you might not want the identity to evaluate to true because you know it's true, otherwise we wouldn't have given it to you. So you might want to use it in a slightly unevaluated form, like I apply it to argument C and I get a conditional expression. Or here, give me all elliptic E's that do not contain elliptic K within indefinite integrals. And here I get a nice result. And I can nicely select what I want with respect to type as well as what functions occur. We have also built-in function formula data that is for algebraic physics formulas. Like give me Ohm's law, and you get it again as quantity variables. You can plug in values, and you can search them, and you can nicely get them annotated. Should a little bit faster. For instance, you can easily search for, give me all formulas that either contain the speed of light, the Planck constant, or the gravitational constant. So here's this famous Okun cube. And you can easily construct them, and there are 107 of them, and then you can put them into a coordinate system with speed of light, Planck constant, and gravity, and you see what are all the formulas that are out there in this exponent space. There are many physical systems, as I already mentioned, and some of them are actually quite non-trivial. I come back to an example slightly later. So why do we have entity value on the one side and star data function? It seems a little bit not totally consistent. There are two reasons for this. One is important domains are in the Wolfram language. So they have a star data because it's something that everybody knows, like a country or color or city is something that really occurs a lot in the real world, people care about, and we have them as built-in functions. But then there are many exotic things that, like cat breeds. It's arguable that cat breeds is not the most important thing, so we have them in entity value, but we don't have them as a star data function. On the other side, we want, of course, to continue the tradition of the data packlets to provide the functionality that we always have provided. Okay, in the spirit of time, I skipped this example. And then there's a second reason why we have star data functions. Some of the star data functions are not just of this relatively rectangular form, entity and property, but they are more complicated. You might have to give additional parameters, like you might have to give times, positions, other values, like air pressure data. Air pressure of what? Of course, of a geographic position, so we need a function that has a different argument structure than entity value. Similar for a large variety of other functions. Or thermodynamic data. You have a certain material, you want to know at a certain pressure and temperature what is its density. That wouldn't fit very nicely. And there are things like geo-elevation. You want to know what's the height of the Earth at a certain point. Like here, I take from the whole world the geo-elevation data at a certain zoom level, and I make a histogram of the heights, and not unexpectedly it has a gigantic maximum at 0, which basically means at sea level, because the water is permanently eroding the coastline and makes it very big. That's why we have a lot of values here. The similar pictures, say, from Moon or Mars would look much more uniform and would not have such a maximum. Or human growth. Human growth, you have to specify how old is the person, what is the gender, what is its stature, and you can calculate a lot of things. Like here's a cross distribution in the height and weight plane of humans. Like humans are in height probably much normal distributed, but they are log normal distributed in weight. And there's a simple correlation coefficient which pretty much correlates the two, and you get this resulting distribution as the bivariate distribution of humans in height and weight. Then there are functions that do not even have star data in their name, but they basically are star data functions. But it would have been too strange to put them in their name. For instance, sunrise. We want to know when the sun rises. It's not sunrise data. While one could argue that in the past it has been recorded, it is the data. There's no reason to doubt that in the next few hundred years the sun will still rise according to the laws of Kepler. And then there are things like solar eclipses. Solar eclipses are in some sense a type of data, because obviously they occur, they span a certain time, they span a certain amount of area, so we have them as its own function, solar eclipse, which you can take the polygon and draw it, say, on a map. And then there are external data. External data are things that we currently don't have, that change very fast, that are owned by somebody else. For instance, here's a connection to Wikipedia. I ask for what kind of geographic things are near to a certain geographic object, for instance this canal. I get a long list, I can immediately plot them. Or Flickr, I can say, give me a couple hundred pictures from people that were made near the Lenin Mausoleum. Or I can ask the Open Library Service Connect, give me all books from Leo Tolstoy, when they were first printed. I can make a timeline quickly. So it's very nice how all the functions quickly work together. And then, what I had mentioned in the beginning, we must access sometimes things not through a function, but through a piece of text that we get from somewhere. And for this, we have either the Wolfram alpha function that you can put any string in, or we have this new functions interpreter, which you say the domain and you say your string, and then you get the canonicalized version back. Like here's a city Ufa from that you get canonicalized back. Or sometimes you just have a picture, like here's a picture, and I say image identify. I assume I know it's a mammal. What is it? It's a rhino. Yeah, this seems right. We're actually pretty good with recognizing animals. So, a couple minutes left. So I have a set of examples. There's not enough time to go through all of them. So let's just go through a few of them. Assume somebody gives you £1 bag of US coins, and assume the £1 is measured within 0.1%, which seems reasonable for a decent supermarket scale. And somebody asked, what's the value of this? And it's a very nice calculation, because the first thing is we must find what kind of coins could be inside. After we know what kinds of coins could be inside, we need their weights. So here are the coins. Coins are very much standardized, and their weight does obey around 3-4 digits. So we have the weights. But now comes the real calculation. How do we calculate all possibilities? And there's this very nice function for Boolean solve, which gives you all possible solutions of linear integer equations. So we call this, and we get around 11 or 10,500,000 possible solutions. We calculate them all, and then we make a histogram of the value. So there seems to be, if we are unlucky, we just have something like $3. If we are lucky, we have something like $55. But probably the bag is around $20. And we can also put it in the number of coins versus the dollar amount in a nice 3D histogram plot. Let's skip this one too. This is a fine one. There was a nice paper last year about what is the relation between the speed of sport balls versus their masses in radii. So we know a lot about sport balls, like here's a proper FIFA soccer ball. We know their areas, their masses, their top speeds. And so we take all balls, the entity class of balls. Here are they that are standardized. We get their speed, their mass, and an image. And then we plot them, and indeed, it looks pretty much like there is some kind of exponential law here. A golf ball can be really fast, but it's a very light ball, and there are here very heavy shot balls. We cannot get them too fast. And then we can even try to fit a logarithmic law to them, and then we have a nice conjecture that we can test on yet another ball if we add one. So thermodynamic data, quick example, say we have air, we have it at a pressure of 0.2 megapascal and 300 Kelvin. We get a list of all things we can say about it. There's a lot. But more interestingly, I won't say in the TV diagram, typically one only sees the PT, where is nitrogen at the same time liquid and gas and coexisting. So it takes a little bit of code, but then I can make a very nice picture with the critical points and the phase boundaries. Let's find all names of Russian cities so that somewhere in the world there is a city with the same name. So I get all cities from Russia, and then I take the name out and get all with the same name, and then I see here, mouse over the shoot. What is here? There's a same named in Tajikistan, in Kazakhstan, in the Ukraine, Kazakhstan again, Belarus, Ukraine, Tajikistan. this actually, obviously, this picture is a little bit more interesting if you make it with the US, because so many immigrants over the last few hundred years brought their city names from the whole world, and you find basically every big capital of the world in some little village represented in America. So let's skip this one. Yeah. No, let's skip this one too. It's not enough time. Here's the interesting one. The example of the physical system. I had already mentioned the charged physical systems. Let's start with a simple one, a rectangular sheet. So here's a rectangular sheet, and I get its potential. It's not a difficult function, but also not an easy function. So it takes a little bit. So I can get rid of the units just for visualizations, for quickness, and plot the resulting equipotential lines. Okay, now slightly more complicated. Take a charged cube. A charged cube, so we basically have a homogeneous density, and we calculate its potential. This integral is doable, but not straightforwardly. It will take you already a little bit. Mathematica cannot do it out of the box. So we get a result that's already a little bit longer. And then we can again de-dimensionalize it, plot it, and we see the maximal field strength is on the edges of a cube. Not unexpected. Now we can compile it so that it's fast, and then we can say build a manipulate, and we can have a satellite orbiting. Let's see if this works. Yeah, we can have a satellite orbiting a cube, and we can either have it reflected when it hits the boundary, or we can let it go through if it's a smooth material. And we can change the initial condition. So we can use for periodic orbits. That's a non-trivial problem in such potentials. An interesting one. Or let's do something more interesting, like let's take the Wolfram Alpha logo and let's see how a satellite would orbit a Wolfram Alpha logo. So the easy part is take the Wolfram Alpha logo. That's a rhombic hexacontrahedron. And here is a picture of it made from individual tetrahedra. Now the complicated part is what's the gravitational potential of a massive tetrahedron. And it's actually interesting. There are around a dozen papers over the last 15 years written about the subject. And I had an intern last year. I said, we really should have this. Could you implement this potential? And it turned out that virtually all of the papers had somewhere a typo. And it took him actually a couple of weeks before he finally had a version that's really correct. It's actually not too difficult, because what you do is you use repeatedly Green's theorem to change every volume integration to a lower dimensional one. So you go from the full tetrahedron to the faces of the tetrahedron, from the faces of the tetrahedron to the edges of the tetrahedron, and then only the edges matter. And then you get this formula. So it's not short, but it isn't terribly long either. So you can use it. Fully expanded, it's a pretty big formula of around 4 meg. But then you can visualize it. And here is basically the equipotential lines of a Wolfram Alpha logo. And then you could continue and fly satellites around it. Let's skip this one in the interest of times. That's an interesting one. So I've spoken a lot about units. Natural question is, how do you measure something? And it turns out there are, of course, many measurement devices in the world, but there aren't too many, on the order of 1,000. And we have maybe 2/3 of them. So we collected them carefully, so we know what kind of devices out there, what do they measure, what range do they measure, how precise are they. And you can then, again, make some nice graphics showing the space of dimensions, say length versus time, and then you can visualize what is available, what you can measure in this corner of the world. the next page has a big graphics. That's why it's a little bit slow to go there. Okay, here we go. But you can also do what is becoming increasingly popular called digital humanities, not just natural science. Let's take artworks. So let's get a set of paintings and let's look at them. Let's compare a couple painters. We can say, take this set, Bosch, Titian, Rembrandt, Vermeer, Cézanne, Van Gogh, and we get all of their artworks. Here we have a count of them, and then we can plot them, say, how big did they typically plot, at which time. And we can also embed them, say, in a color space and see in a color triangle, like here's very pale blue, this Monet, Paul Klee is really, really red, he is really green. So you can do a lot of interesting things with paintings, which typically isn't analyzed programmatically. Then you have also some fun, and then we slowly come to the end. For instance, you can ask, what's the Superman insignia? And you get a picture, but there's not only a picture, there's also a nice formula associated with it. Now you can take two of them, one say in the XY and one in the XZ direction, and then you can make a Superman solid. From various directions you can look at it, and it is the sign of Superman. And then, as the last example, we have something that we call popular curves. Here is a soldier called Zweig from Czech Republic, who was very famous in World War I as a cartoon character, and we have a closed form for him, and you can play around with these curves. There are a large amount of these curves that we have. Here are some popular classes, Simpsons, superheroes. And then you can amuse yourself by, say, taking yoga curves, modify them, or you take the US president and raise them to a power. Yes. Power 1, he looks probably most normal, but you can take its square root or a square. And you can do this, of course, with and you can it's just a couple lines of code to write such a fun program. Okay, so that's a rough overview over the Wolfram Language data world. So what's coming in the future? More data, especially non-US. There are various areas where we are pretty good with data about the US, but not so good with data about the rest of the world. We are working on this. Then more direct, I showed the implicit entity and faster data access, more connections between the data, and more efficient handling and returning. Various new star data functions are to be expected, many more domains. Then there will be things like you have a 3 millimeter sphere of gold. We have a sphere, we have gold, but we don't have currently something to unite it. So there will be something to build such an object directly from primitives and do something with it. Then more integration of large databases, especially external ones. And with respect to units, while we have many units, currently all our calculations are done just in SI. Obviously, physicists want to do units in what they call natural coordinates, Planck, Bohr, atomic. So we have to work on this. With respect to geography, there are many more planets to be added, higher resolution data sets, different kinds of data sets. So it's a direction we hope to continue pretty intense over the next years to make much more data available and have them seamlessly integrated and easy to use for real life models and applications. Thank you very much.
Hi, Michael. Can you hear me?
I can hear you, Galina.
Fabulous. Thank you so much. That was an awesome presentation. I think we've all enjoyed it quite a bit. So I'm going to ask the audience here if they have any questions. Желательно спрашивайте ваши вопросы на английском языке, чтобы вас Майкл понял, но если уж не получается, то я попробую перевести. У кого есть вопросы? All right, hold on.
Hi, Michael.
Hello.
My name is Roman, and I have no question, but I want to say you bravo and thank you for your job, for your Mathematica programming books, and for all what you do with Wolfram blog and in this presentation and your other jobs.
Thank you very much.
That's all.
I'm glad
Thank you.
you liked it.
Well, that was an easy question.
Yes.
Does anyone else want to say something, ask any questions while we have Michael here with us?